Last time we were talking about triglyceride metabolism. Recall that we figured out how to hydrolyze the esters in the triglyceride from lipase. We figured out how to convert glycerol into dihydroxyacetone phosphate, which you will see is one of the intermediates in glycolysis. That was by phosphorylating one of the OH groups and then oxidizing the secondary alcohol to a ketone. And then the other thing you get from the triglyceride is 3 fatty acids. And we wanted to start to talk about fatty acid metabolism. And this is the step we did so far. You've got the carboxylate, which, as you recall, is unreactive as an electrophile. That's sort of level 4 carbonyl compound reactivity, meaning not reactive as an electrophile. And we want to convert it into a thioester. Recall that thioesters are level 1, very reactive as electrophiles. So this is going to be uphill, and so it's no surprise that we have to consume ATP to make this happen. The enzyme that does this is called long-chain fatty acyl-CoA synthetase, or alternatively ligase is another word that's used. The term synthetase is usually reserved for enzymes that make new bonds and consume ATP to make it happen. And we use also coenzyme A to make the thioester. I think you've seen coenzyme A before, but I'm drawing it for you here again. You should be able to pick it out of a lineup, but you don't necessarily need to be able to draw its structure. You shouldn't need to be able to draw its structure from memory. Coenzyme A is basically a thiol with a long handle for the enzyme to hold on to. There are 3 portions of coenzyme A that might be interesting to you. This portion comes from ATP. You can see the adenine base, the ribose ring. You can see a phosphoanhydride bond. You can also see an unusual phosphate that's on the 3' hydroxyl where it normally isn't for ATP. The next segment highlighted in purple comes from pantothenic acid, which is vitamin B5, and you get that in things that you eat. So if you ever see vitamin B5, you can think, oh, that's how my body makes coenzyme A. And then this portion, the aminothiol with 2 carbons in between, that comes from the amino acid cysteine. If you imagine a carboxylate being on this carbon, then it's cysteine, right? Carboxylate, alpha carbon, nitrogen, carbon, and then sulfur. It's formed from decarboxylation of cysteine, probably through a PLP-mediated process like we saw before with making dopamine or serotonin or histamine. You can decarboxylate amino acids to get amines, and this aminothiol comes from that. For our purposes, it's just, again, a really long handle for the enzyme to hold on to, and then a thiol, which is a good nucleophile. So what we talked about last time was that the fatty acid first, the carboxylate, as a nucleophile, attacks the alpha phosphoryl group of ATP. The enzyme activates that alpha phosphoryl group. Notice this is different reactivity from kinases. Kinases activate the gamma phosphate group. So this is sort of a unique way of doing things. The enzyme activates that. There's likely magnesium binding here to this 2-phosphate unit, pyrophosphate, making it a good leaving group. Here's the pentavalent intermediate where phosphorus is bonded to 5 things. It's kind of carbonyl-like chemistry. Nucleophile attacks phosphorus, electrons kick up. Then once you have this intermediate, they kick back down and the pyrophosphate leaving group leaves. And that generates an intermediate called a fatty acyl AMP. It's a acyl phosphate or a mixed phosphorus carbon anhydride. Basically, you've converted the oxygen on the carboxylate into something that is now a good leaving group. So nature is using ATP to activate the carboxylic acid so that it can be a good electrophile. Another thing that happens downstream is that the pyrophosphate leaving group gets hydrolyzed from pyrophosphate to 2 phosphate groups. You're breaking a phosphoanhydride bond, and you're making the phosphate groups, which are at about the same level of reactivity as a carboxylate. So you're going from something that's around level 1 in reactivity to level 4. So this is very downhill. I don't actually know whether this happens spontaneously in the cytosol or whether there's an enzyme that helps it happen. But either way, it helps make this reaction favorable. Nature does this a lot, coupling some reactions to others that are even more downhill to push things forward. So at this stage, we're not done yet. This intermediate is still bound to the enzyme, but now the carboxylate is activated with a really good leaving group, so now we're ready for coenzyme A thiol to come in and act as a nucleophile. Okay, questions about that? All right, let's take the fatty acyl AMP. This again happens in the same enzyme active site. And then coenzyme A binds in the enzyme active site, and a base from the enzyme deprotonates coenzyme A thiol, and then the thiolate attacks the carbonyl carbon, and you get a tetrahedral intermediate. Here, what we're going to see is exactly what we would expect for nucleophilic acyl substitution. I'm going to abbreviate that AMP leaving group in green on the left, just as OAMP to simplify our drawing. Electrons will kick down, AMP will leave, and that will give us our fatty acyl CoA, which is a thioester. And then the other thing that is produced is AMP as a leaving group, which we probably don't need to draw, but I will just briefly here because I want to make a point about the reaction. Whoa, and this is the adenine base. Okay, so the fatty acyl CoA synthetase activates the carboxylate as the AMP acyl phosphate by attack of the carboxylate on the alpha phosphoryl group. Then, in a second step, coenzyme A attacks the acyl phosphate. You just get classical nucleophilic acyl substitution to give you your thioester. As we look at this reaction, it looks as though we're only consuming one molecule of ATP, because we only put one molecule of ATP in. It turns out, as far as metabolism is concerned, we've sort of consumed two. And that's confusing until you look at the details. First, look at how many phosphoanhydride bonds we broke in this process. We broke one here between the alpha phosphate phosphoryl group and the beta phosphoryl group when the enzyme activated the alpha phosphate group and the carboxylate attack. So that's the first one. The second one is here when we hydrolyze pyrophosphate. So we've broken two phosphoanhydride bonds. Now, why does that end up consuming two equivalents of ATP? The thing you need to understand about both substrate level phosphorylation and oxidative phosphorylation is they both act on ADP. In substrate level phosphorylation, this occurs in glycolysis and in the citric acid cycle. Basically, ADP or something like it with two phosphate groups on it attacks a phosphate group on another molecule, and you make a new phosphoanhydride bond. You have to start with ADP and not with AMP. Similarly, in oxidative phosphorylation in mitochondria, ADP binds the ATP synthase, and then a phosphate group gets added. There's no way for AMP to bind that ATP synthase. So if you have AMP, The only way to recover it is to convert it into ADP with another equivalent of ATP. And then you have 2 molecules of ADP that you can then take and phosphorylate. So really this metabolic mechanism activating the carboxylic acid, activating the fatty acid carboxylate consumes basically 2 ATP molecules. The first one is here, and then the second one is here, generating 2 equivalents of ADP, right? Does that sort of make sense? So it's not such a big deal, but at some point you'll face some questions in the textbook about, okay, here's this fatty acid. How many molecules of ATP do I get from metabolizing that fatty acid from the very beginning all the way to the end of the citric acid cycle? You'll get the wrong answer if you don't realize that you're down 2 molecules of ATP at this point. All right, so now we're ready for beta oxidation. Beta oxidation is the process of clipping off 2 carbon units from the fatty acid and converting them to acetyl-CoA. It's an iterative process. You will see that if I have a 2, 4, 6, 8, 10, 12, 16, 2, 4, 6, 8, 12, 14, 16. If I have a 16 carbon fatty acyl-CoA, you're going to see that we're going to go through this process of fatty acid beta oxidation. 1, 2, 3, 4, 5, 6, 7 times. And in the end, we're going to get 8 molecules of acetyl-CoA. So that's the overall goal. So let's go through one round of fatty acid beta oxidation. Again, as I've said with metabolism, if you have eyes to see, you'll see the hand of God in this, because it just makes sense why things have to be this way. Okay, so the first step of fatty acid beta oxidation, and I'm going to just draw the last 2 carbon units of a long chain fatty acid. The first step of fatty acid beta oxidation is catalyzed by an enzyme and uses the molecule FAD to do the oxidation chemistry. And the product is an alpha-beta unsaturated thioester. And you will see that the H2 that gets transferred to the FAD molecule is really from this hydrogen and this hydride. So in the first step of the mechanism, the enzyme removes the proton from the alpha carbon of the thioester. That's just enolate formation. Okay. In the second step, the lone pair electrons on the alpha carbon are going to kick down and kick off the hydride, which is going to be delivered to our oxidizing agent, which is FAD. FAD you probably haven't seen before, and once you see it, you'll hope to never see it again. Unfortunately, it shows up in the citric acid cycle. It's like NAD+, only it's neutral and it's more complicated than NAD+. So this portion of FAD that I'm drawing is where FAD gets the letter F. The molecule that I'm drawing here is called flavin. And you may have heard of riboflavin, as if you read cereal boxes, some of these are fortified with riboflavin, and that riboflavin contains this functional group. The nitrogen is attached to a ribose ring. That's the ribo part of riboflavin. And then you have a phosphate bonded to another phosphate. And then that second phosphate is bonded to another ribose ring. And then you've got adenine here. So the F part of FAD is this part, the flavin. The A is for adenine, and then the D is for dinucleotide. And a nucleotide is where you have a base, a ribose ring, and a phosphate. So you can see this is a nucleotide and this is a nucleotide. They're bonded together, and that's where the dinucleotide comes from. Ever after, when we draw FAD, we're just going to put a big R group here and forget about all of this. You should be able to pick FAD out of a lineup, but you don't necessarily need to have been able to draw its structure from memory. Yeah?
So would that lone pair kick off the hydrogen if FAD wasn't there?
No, the lone pair would not kick off the hydrogen if FAD wasn't there, because hydride is a terrible, horrible, no good, very bad leaving group. So you need a hydride acceptor sitting right there to take the hydride as it leaves.
So in that case, like, why is the mechanism the lone pair kicking it off and not FAD taking it?
We're going to show, I haven't showed you the part where FAD takes it. I'm going there.
Oh, okay.
Yeah. Yep. So looking at FAD, and somebody told me before, a previous time I taught the class, that it's really annoying when my notes span pages, because then they export it as PDF and there's some weirdness. So this one's for you. All right, look at FAD. This nitrogen, which I'm going to highlight in pink, is electron poor. It's not immediately obvious that it's electron poor like it was for NAD+, but I want you to look at where it is. Carbonyl carbon, alpha carbon, the nitrogen's at a beta position. You've said before, we learned this before, that alpha beta unsaturated carbonyl compounds are electrophilic at the beta carbon. And one reason for that is we can draw a resonance structure with a negative charge on the carbonyl oxygen and a positive charge on the atom at the beta position. So that carbon is electron, that nitrogen is electron poor. The other reason it's electron poor is the same reason that nitrogen is actually conjugated to another carbonyl, alpha, beta, gamma, and delta, and we can similarly draw a resonance structure where we put a negative charge on this carbon and a positive charge on that nitrogen. So hopefully you can see that those two carbonyls here and here make the nitrogen that I've highlighted in pink electrophilic, and it's a hydride acceptor. So as the lone pair kicks off the hydride, that hydride is accepted by FAD. Then these electrons go here, and these pick up a proton from the enzyme. And the product of this mechanistic step is the alpha beta unsaturated carbonyl compound, where we now have a pi bond between alpha and beta carbons. And we now have FADH2. I'm just going to draw the flavin part of the molecule. Oops. R group here. This H that I just drew is the hydride that was delivered. This is the proton that got picked up. This is the hydride that was delivered. And you can see that this is why the enzyme that does this process, well, actually, I was going to ask you that. What do you think the enzyme's name is? What do you think, what would be the class of enzyme you would give for this reaction? Transferase, because you're transferring, that would be a good one. I've also heard people say, well, is it oxidase, because you're oxidizing something? Well, those aren't bad guesses, but it's a dehydrogenase because you take you take a proton and a hydride from this molecule, you dehydrogenate it, and where does that hydrogen go? That goes to FADH2. Okay, FADH2 can deliver hydride and its electrons to the electron transport chain. You can use it to drive the proton gradient in mitochondria and generate ATP at the rate of about 1.5 ATPs per molecule of FADH2 that delivers to the electron transport chain. This is one of the reasons why this process is called beta oxidation, because we've oxidized the beta carbon. It used to be at the alkane oxidation state. Now it's at the alkene oxidation state. The other thing this first step does is it sets us up to do more things at the beta carbon. You'll see the chemical logic in just a little bit. The next step is to do conjugate addition. So that first step was oxidation to an alpha beta unsaturated, to get an alpha beta unsaturated thioester. The second step will be conjugate addition of water to the alpha beta unsaturated carbonyl compound. We've heard of these before. Do you remember where alpha beta unsaturated carbonyl compounds are electrophilic? Two places. What are they? Yeah, the carbonyl carbon, that's 1,2 addition, and the beta carbon, which is 1,4 addition. So the enzyme is going to direct water to attack the beta carbon, and you'll see why it's really useful to have an oxygen at the beta carbon as we get to steps 3 and 4. The enzyme deprotonates water. We attack the beta carbon. Normally, if we did conjugate addition, we would draw the mechanism like this. A nucleophile would attack the beta carbon, then we would have a new bond between the nucleophile and the beta carbon, and we draw an enolate intermediate with a negative charge on the alpha carbon. We could do that here, but sometimes in enzyme catalyzed mechanisms we simplify, in part because one of the roles of enzymes is to make reactions faster and easier, and one of the ways they do that is by protonating things to turn them into good leaving groups, and or protonating negative charges as they arise, sort of greasing the wheels, because charged intermediates are higher in energy, and so if you can protonate them, maybe the reaction goes faster. So rather than draw an arrow like this and then drawing a separate enolate intermediate, one of the things we can do here, and that would not be wrong, you're totally free to do that, but one of the things we can do to save time is to show that enolate getting protonated on the alpha carbon by some enzyme acidic side chain, all in the same step. Sometimes we have evidence for this kind of thing to happen. Other times we are assuming it happens, or we're just writing all the steps in the same steps so we don't have to draw these large molecules multiple times. So this is a little bit of freedom you have when you're drawing enzyme reactive mechanisms. You can dig into the data and see what the mechanistic data support, but in a case like this where we know it's conjugate addition, you can skip drawing the enolate intermediate and just show it getting protonated as it forms. So the product of this reaction would be an OH group on the beta carbon, and then our coenzyme A thiol. So we've converted our alpha beta unsaturated thioester into a beta hydroxy carbonyl compound. And we've now got an oxygen on the beta carbon. This is another reason why we call this beta oxidation. Now, if you look at the beta hydroxycarbonyl compound, it should look somewhat familiar because that's a product of what kind of reaction that we learned this semester? Beta hydroxycarbonyl compound is a what product? Not Claisen, close. What's the other word? Aldol, right? And we've done retroaldol reactions. The bond that's made in an aldol reaction is this bond between alpha and beta carbons. You can see that if we did a retroaldol reaction at this point and broke this bond, what would the functional group be on this carbon? An aldehyde. You can tell that it's an aldehyde because in the aldol product, this used to be the carbonyl carbon, this used to be the carbonyl oxygen, and the carbonyl carbon's attached to a carbon and a hydrogen, so it'd be an aldehyde. Now remember, our goal is not to make a fatty aldehyde, we want to make a fatty acyl thioester. So it would be unwise to do a retroaldol at this stage, but there's one modification we can do, there's one reaction we can do that's going to set us up to do a retro type reaction to break this bond between alpha and beta carbons. But you'll see first we need to oxidize this OH group to a ketone. So the next step is an NADH based oxidation, NAD plus, sorry, based oxidation of the beta hydroxy thioester to form the ketone at the beta carbon. And this reaction uses NAD plus as the oxidizing agent. You get reduced NADH out and a proton needs to be removed. That's all this means here with the H plus. We do not mean that a proton's floating off into space, rather it gets removed by some group in the enzyme active site. The product is going to have now a ketone at the beta carbon. So the product will be a beta keto thioester. This is just a simple NAD plus based oxidation. I'll draw this briefly. I probably won't draw this mechanism again because you've seen it before. And every other NADH based mechanism is going to follow this pattern. A base removes the proton from the alcohol, electrons kick down, and hydride gets delivered to NAD plus like this. So you make NAD plus, the hydride from the beta carbon ends up on NADH. The proton that's removed by the enzyme active site is the one from the alcohol. Okay. So that's a third oxidation, or that's a second oxidation step. If you're keeping track of doing the accounting for energy-rich molecules that we've generated, FADH2 is one and NADH is another. Now, with the beta keto thioester in place, we are ready to do a retro-Claisen reaction. I asked at 9 a.m., you guys remember what the Claisen reaction was? And there were blank stares and no. And I told them, you probably should figure that out in the next couple weeks before you take the final. You want to remember that. But it's okay, I know how it is. Go ahead.
Where will we find this?
So the Claisen reaction, you can look it up. It is in chapter 18. And just as a quick review, in the Claisen reaction, you started with an ester. You made, with a pretty weak base, a very small amount of enolate. Then that enolate reacted with another equivalent of ester, attacking the carbonyl carbon. This is the aldol-like step of enolate, attacks carbonyl carbon. That makes a new bond between the alpha carbon of the enolate and the carbonyl carbon of the electrophile. But you have something that's a decent enough leaving group relative to a negatively charged oxygen to kick off ethoxide, and the product is this beta keto ester. Now, in the lab, the leaving group that left in that last step is OET minus, and it's a pretty good base. And the pKa of this proton that's alpha to 2 carbonyls is around 13. So it's pretty easy for lone pairs on ethoxide to deprotonate. And that's what ultimately drives the reaction forward. That's the sort of thermodynamic sink that the molecule falls into. Otherwise, you could imagine the reaction being reversible. What if ethoxide attacked at the ketone? That's reasonable if that proton weren't there. But if ethoxide attacked at the ketone, you would go back to this tetrahedral intermediate, and then what if the electrons kicking down didn't kick off OET minus, but kicked off the enolate as a leaving group? That's called the retroclaisen reaction. So going in this direction would be called the retroclaisen. In the lab, the retroclaisen doesn't happen very much, or at all, because it's blocked by the acidity of that proton and the basicity of the leaving group. You're going to see, though, that nature is able to overcome that with this thioester. So the last step of beta oxidation, or the last step in the sort of cycle of beta oxidation, is a retroclaisen. And we're going to use coenzyme A as a nucleophile. We're going to break the bond between the alpha and the beta carbons. And I'm going to just highlight the 2 carbons. We're going to make 2 products. The 2 carbons in pink are going to become acetyl-CoA, except we can't spell. There we go. And then what will be left over here is what I will call a truncated fatty acyl-CoA. It's 2 carbons shorter than it was when we started, and I'm going to put this in parentheses, in air quotes, though I guess when I write them they're no longer air quotes. That used to be the beta carbon. Okay? So just think of that by analogy to what I've shown you above. What would happen if this nucleophile attacked the ketone, then the tetrahedral intermediate kicked off the enolate, then you'd end up with 2 molecules, and that's exactly what we're doing here. Okay, any questions about the claisen? You can review that in chapter 18. Probably a good idea to do if you've forgotten totally about it. All right, so let's show you how this reaction happens. It's kind of interesting in that some of what goes on, well, at least some of the amino acid side chains in the active site that participate in this are known. A base from the enzyme active site, a histidine residue, though I'm not going to draw it, deprotonates a cysteine side chain in the active site, and then that cysteine attacks the beta carbon to get a tetrahedral intermediate. It looks like this, negative charge on the oxygen. Here is the cysteine side chain thiol. Here is the bond between beta and alpha carbons. And then here is the rest of the molecule. Now, if electrons kick down from the carbonyl oxygen, they could kick off the cysteine as a leaving group. That's just the backward step. What if instead they kicked off the enolate as a leaving group? Okay. Now, we're going to do what we did for the conjugate addition step, where instead of showing an enolate forming, we're going to have it be protonated by the enzyme active site. As electrons kick down and the enolate leaves, we're going to have it pick up a proton from some side chain in the enzyme active site. That's going to get rid of acetyl-CoA. And then you will see that our, what used to be the beta carbon is now a thioester that is linked to the enzyme. So you have this enzyme-linked thioester. This is the old beta carbon, and this is acetyl-CoA. So we've done part of what we set out to do. We've clipped off 2 carbons as acetyl-CoA. Questions about that? Now all that's left is a simple nucleophilic acyl substitution reaction. We want to swap out, we want to liberate the fatty acyl thioester from the enzyme so that the enzyme can do additional chemistry. And so a base will remove the proton from coenzyme A, which will attack the carbonyl carbon. That's going to generate a tetrahedral intermediate, where this is the cysteine residue and this is the coenzyme A thiol. Then electrons kick down, cysteine thiol leaves, and you end up with your truncated acyl-CoA, where this used to be the beta carbon. Yes?
Could you just go up just a bit?
All right, so to summarize beta oxidation, we first used FAD to create a pi bond between alpha and beta carbons. That was an oxidation step. Then we did a conjugate addition of water to get the alcohol of the beta carbon. Then we oxidized that alcohol to the ketone. Then we did the retroclaisen reaction. 4 steps: oxidation, addition of water, oxidation, retroclaisen. And you'll see that now we get to the truncated fat acyl-CoA. This is now the substrate for another round of step 1. So go from here all the way back to step 1, and we do it again. And we do it again and again and again until we've converted this 16 carbon acyl-CoA into 8 molecules of acetyl-CoA. By the way, 16 carbons, 8 units of acetyl-CoA. How come I'm saying you only go through beta oxidation 7 times? Because the last one also gets clipped off as acetyl-CoA, right? So let's sort of summarize the yield from this process. From the 16 carbon carboxylate, which I'm just going to draw here, we lose 2 molecules of ATP to get to the acyl-CoA. And then we do 7 rounds of beta oxidation to make 8 molecules of acetyl-CoA. Now, in beta oxidation, in those 7 rounds of beta oxidation, how many molecules of NADH do we make per round of beta oxidation? Scroll back and look. Yeah, we just make the NADH in the alcohol oxidation step. And how many molecules of FADH2 do we make? Also 1. We just make that in making the alpha beta unsaturated carbonyl compound. So we're going to get 7 NADHs and 7, I guess the FADH2 comes first, then the NADH. And then 7 molecules of FADH2. And then those 8 acetyl-CoAs are going to go to the citric acid cycle. And in the citric acid cycle, each carbon will be oxidized to CO2. we're going to make some more NADH, FADH2, and some more GTP, which can be exchanged for ATP. So we're not really quite ready quite yet to say what the total yield from a fatty acid is, though we can say what we've gotten so far to this stage. It turns out that in the electron transport chain, the exchange rate for FADH2 is about, for every molecule of FADH2, you get about 1 molecule of ATP for each FADH2. And for NADH, 1.5 molecules of ATP. For NADH, you get about 2.5 molecules of ATP. Why is it that it's a fraction? Why is it 2.5 instead of an integer? It's not a one-to-one thing. NADH and FADH2 deliver electrons to the electron transport chain. That drives a proton gradient. Protons get pumped from one side of a mitochondrial membrane to the other. Then they come back in through the ATP synthase, and exactly how many protons get to come back in to make the ATP synthase make ATP and what the concentrations are sort of varies. This is an estimate, and you will see different textbooks use different estimates. Some people don't like 1.5, 2.5, so they'll say 3 and 2 and just move from there. Just make sure whenever you're answering a question from a textbook, either now or in the future about ATP, they'll tell you what the assumed exchange rate is, and this is sort of what we'll use. So far we've lost 2 ATP, but we've gained whatever the math says that number is, which I'm not going to do in my head, but you can figure it out. Okay? Then what we're going to do is show what happens to acetyl-CoA. So by the end of all of this, you'll be able to take an 18 or 16 or 14 carbon fatty acid and tell me exactly how many molecules of ATP you get from it. And that'll give you a sense for why fats are so rich in calories. I mean, this is literally what we're talking about, how many ATPs you can make from a triglyceride. Yes?
Why is the NADH producing more?
Yeah, why does the NADH produce more? It turns out NADH enters the electron transport chain at the beginning. FADH2, its reduction potential is a little bit lower than NADH, and it enters at a lower point, and so it doesn't drive as much transport of protons across the mitochondrial membrane. All right, so we could jump right to the citric acid cycle and explore the fate of acetyl-CoA. However, carbohydrate metabolism also generates acetyl-CoA, and so what I'd like to do is go back to carbohydrates, take them all the way through to acetyl-CoA. We'll join the 2 pathways up, and then we'll move on from there. So the pathway for carbohydrates, starting with glucose, is a process called glycolysis. This happens in the cytosol, and if you learned in biology in school about anaerobic respiration, glycolysis is what really they mean when they're talking about this. In the citric acid cycle, ultimately the NADH that you generate and the FAD go to the electron transport chain, and the thing that ultimately accepts the electrons is oxygen. Your body literally reduces oxygen to water. That's why you have to breathe oxygen. Glycolysis doesn't involve oxygen as an acceptor of electrons, so it can happen even if you don't have oxygen. Though, as you know, your body can't keep up with its demand for ATP simply with glycolysis alone. You need the citric acid cycle to generate enough for you to proceed. But we'll start with glycolysis, and this begins with glucose. We won't be too careful about whether we're dealing with the alpha or the beta anomer. Glycolysis is a 9-step process, which we're going to do all in the next 5 minutes. I'm kidding. Just kidding. Okay, nervous laughter. That's like, it wasn't really that funny, but we're going to use ATP, and we're going to transfer the gamma phosphoryl group of ATP from ATP to the C6 hydroxyl group of glucose. The product looks like this. Everything's still in the same place, and the C6 hydroxyl is now a phosphoester. You take a phosphoanhydride bond from ATP, and you transfer that gamma phosphoryl group from ATP to the C6 hydroxyl, making a phosphoester. Make a prediction. Is that uphill, downhill in energy, or just basically no change in energy? Okay. A little bit of controversy. We're not sure. Okay. We started with an alcohol and a phosphoanhydride. What level of reactivity is the phosphoanhydride? Level 1, highest. We convert that phosphoanhydride bond between the gamma phosphoryl unit of ATP and the beta unit into a phosphoester. What level of reactivity is a phosphoester? Number 2. That's a little bit lower, right? Just in the same way that esters are lower in energy than acid chlorides or anhydrides, so phosphoesters are lower in energy than phosphoanhydrides. So this is downhill. The free energy change of this reaction in the cell is estimated as being something close to -8 kilocalories per mole. And that is essentially irreversible. That's a hill that you can't climb back up. And again, you can recognize irreversible steps in metabolism by just comparing the reactivity of the starting materials versus the products. Am I going uphill versus downhill? Let's actually jump and do that same comparison with the first step that we talked about today, using the fatty acyl-CoA synthetase. Is this uphill, downhill, or sort of neutral? Start out with a phosphoanhydride in ATP and a carboxylate. You make a thioester. So you would say it's neutral, but perhaps if you also included what happens to the pyrophosphate, then maybe you'd say it's downhill in energy. Again, we're just looking for a general sense for whether reactions are favorable or not by comparing the reactivity of starting materials versus products. So, phosphoanhydride to phosphoester, that's very downhill, it's irreversible. What that means, by the way, is that when nature does this, it's committed a whole molecule of glucose to this pathway. And your body is not interested in using a whole molecule of glucose if you don't actually need it. It'd like to store it instead, so this step is regulated, right? And we won't talk about the mechanism of how this step is regulated. You'll learn about that in biochemistry. But there are, nature will regulate the enzymes so that this doesn't happen unless, or it can slow down when your body doesn't need it. What kind of enzyme is it that does this reaction, transfers a gamma group? What class of enzyme? Kinase, that's the name for things that transfer gamma phosphates from ATP. Very good. And the enzyme name is hexokinase because it transfers a phosphate group to a hexose sugar. Glucose is an example of a hexose because it has 6 carbons and it is a carbohydrate. Okay, so this first step, you may be wondering, what the heck is nature doing? I thought we wanted to generate ATP, and here we are spending it. It's going to be kind of like fatty acid beta oxidation. You gotta, as Lin-Manuel Miranda once wrote in the musical Hamilton, something about what was it? It's like you don't stay in the game. If you got skin in the game, you stay in the game, but you can't win unless you play the game. Well, you get love for it, you get hate for it. You get nothing if you wait for it, right? My son's 5th grade elementary teacher was awesome. They did this for like the whole last half of the year, they were learning about the American Revolution, and they learned about it through Hamilton. And they put on a play, and so anyway, it was awesome. But we're committed. We got skin in the game now. But we're going to make back our investment. All right, that's enough for today. We'll see you on Monday.